Hello, everybody. We're going to be going through the Chapter 9 PowerPoint here tonight, and we're going to be talking about what they're calling here the principles of computer operations. And just prior to starting this recording, I was just letting the class know that the materials that sit inside of this chapter are really strongly related to the study of what we call computer science, and that is studying computers right down to the bit level and to the machine level and how they functionally do the tasks that they do. And this is important knowledge. Like if you were somebody who was designing microprocessors, for example, or motherboards or RAM or any of those types of things, which some people do professionally, this is really fundamental knowledge and important. In terms of learning objectives, these are listed on the second slide here, which we see. So we're going to kind of talk about all these different topics. And let's kind of start popping through this because there's a lot to go through. The point that they're making here is that we always use computers. We don't really think a lot about what's happening in the background with them. But computers, and this really sticks with me quite a bit. When I first started studying this field, and this was up at Cardinal Stritch University in Milwaukee, I had a professor, Dr. Jim Casson, real brilliant guy. And he was, telling us that computers are very dumb machines. They're circuits and stuff, and they really don't know what to do if you leave them on their own, right? It's all about the instructions that we put inside them. But they, as a functional device, really all they know how to do is add, and every other thing that happens in a computer is a byproduct of computer being able to add. And when you start to think about it mathematically, it becomes pretty interesting because I know I use this example in many of my classes, but addition, if that's the foundation of everything a computer does, how do we get even the other mathematical operations out of it? And the answer to that is, well, what's the inverse of addition? Subtraction. What's the multiplication of addition, right? Well, multiplying, right? If you do, repeated addition, it becomes multiplication. What happens if we do inverse or subtracted actions multiple times? That becomes division and so forth. And from there, we can extrapolate not only all the mathematical functions, but we can also extrapolate things such as letters and numbers and operations and much higher level tasks. And these things are happening in some cases billions of times a second in the background on our computer systems in order to do the things that we see on the screen. And we very much take it for granted. Computing has now become so ubiquitous that there's barely a device that we use that plugs into the wall that doesn't have a microprocessor built into it. Our cars are a perfect example. Some of the modern automobiles that are being produced now, in some cases, have 20, 30, 40 microprocessors on board. That's astounding, considering even 20 years ago, most vehicles did not. If they had a computer, it was one, and it usually ran the fuel injection system, and that was about it. And now we have computers that operate almost every aspect of the vehicle, right down to, like the announcement that Tesla made this week where they're putting their self-driving software into all their models. Not that I recommend that you try it, but pretty interesting. All right, so when we start to talk about computers, we have to look at how they operate, and these are some really important constructs here that we have to look at. So first of all, we look at the processor, the CPU, and what that does. And as it says, that's what executes the instructions. The operating system operates most of the devices on your computer. It controls all the operations, and without it, your computer does not know what to do. The operating system is the most fundamental of all the software on your system. Of course, we run software on top of our operating system. We interchangeably call it software, applications, or in more modern format, ever since we've had mobile devices, we call them apps for short. There's instructions that are embedded into software that people have to create. Cindy, Lou, and Jill, you guys have had experience creating software, and some of you, if you've had your Python class already, or maybe are currently taking it, you're learning that you can create instructions to tell a computer what to do. Part of the instruction set when you get inside of the processor is what we call this fetch execute cycle. And this is more at a fundamental circuit level of how these devices work. Typically our CPU, not typically, but absolutely our CPUs need to interface also with RAM on the computer to allow the instructions to be carried out. So things get loaded into RAM and then something happens, and usually we go from RAM and we store it back to the hard drive or feed it from the hard drive into RAM. But memory is a big part of it. And then of course we have the hardware aspect as well, which are the physical parts of the computer. When you start to look at, like, the applications that you use, and probably the most important collection of applications is your operating system, which is really exactly what it sounds like. It is a collection of applications. The most fundamental part of an operating system, by the way, is this part called the kernel of the operating system, and that's the part that does really all the controlling, both on a hardware and software level, by the way. When you start to look at software, as this points out, and if you could look inside what compromises a piece of software, and you know what, strangely enough, we can totally do that. And this is really bizarre, and I'm going to kind of demonstrate this to you. But I'm going to bring up my basic text editor here on the screen, which is my Notepad++. Okay, so it's on the other screen. No wonder I didn't see it. And if I were to find a folder, for example, that might contain something like an executable file, and it probably have something in here that's an executable file, I'm sure. I'm trying to find one. Here's one right here. I'm going to take this executable file and drop it into Notepad++, a text editor. A big no-no, by the way. But here's the strange thing. Notepad++ will do it anyhow. And what we're getting to look at here, not in terms of binary code, but in terms of higher level machine code, if I look at this file, this is the executable file in a text format. You will see it is still text. Can't read it. I can't make any sense of it. The computer can, and the computer knows how to execute this. But the reality is all the characters that you see here break down to a series of ones and zeros, which represents what we call machine code. And the machine understands what to do with it. We're the ones who can't, right? So we cannot directly create code like this, because this to us looks like nonsense. There's nothing in here that looks like anything we understand. Well, there's a little bit, right? There's a little bit of English there, but very, very little, very, very little. All the rest of it is binary. Now, we do have to write, instructions, and we have to do it in a way that we can understand. But whatever we write as a set of instructions is usually based on some sort of a process of problem solving, usually in the form of an algorithm that can solve the problem, and then is converted to computer code, and then is converted to a binary language that the machine can read. Now, software, when it is created, typically is done in what we call a software stack. And there are layers to software, and this might be a little bit meaningless to some of you right now if you have not had a programming language yet, most notably Python. But for those, and there's at least a couple in the class here that have had some programming and understand how programming works, software is kind of built on layers on top of layers on top of layers. So ultimately it can talk to the operating system, which then talks to the hardware and makes it happen, right? So it's done in this, what we call a software stack. And here's a classic example of a software stack. So when we as programmers learn how to write code, we write code at this level, the very top level. And you'll see some languages being specified here. So this is Visual Basic, C++, C#. I'm assuming JavaScript is what they mean here. But you could also put Python in the mix here too, if you guys are Python programmers. Very rarely do programming languages have the capability to directly interface with the operating system. In fact, in the old days when we used to try to write code, the very first programmers would have to take whatever their instructions were and then convert it into a series of ones and zeros, which we don't do anymore, and then program ENIAC or whatever machine they had on a real base level. Eventually, they moved up to what we called machine language and assembly language, which we're going to talk about here in a little bit, which are more close to English syntax, but still pretty cryptic. But most of those commands were in the form of writing a command to memory, doing addition, recalling something from memory, and those are pretty much the only actions you could really do. As we developed higher level languages, they created basically libraries and tools that we could build on top of. So like one thing you'll see is at the very bottom here we have the operating system, which makes the whole machine go and sends the instructions to the hardware. But most of these languages, when we're coding in them, ultimately, especially compiled languages, use these layers to build the code to the point where we get to the common language runtime, and it's then converted into something the operating system understands. Unfortunately, we do have different operating systems. So, for example, we have the whole Windows, area. Then we have the Macintosh, which is kind of a substrain of Unix or Linux these days, but still is really its own operating system. And then we have all the Linux and Unix platforms, which share a lot of commonalities and a lot of the libraries. But in order for us to write code for those platforms, usually it is specific to the platform, and that's kind of uncomfortable, right? So if I write a program using C++ in Windows, and then I take it over to a Macintosh and try to run the code and compile it, it won't compile. I have to rewrite the code so it works on that platform. It's a little frustrating. There are a couple languages that have exceptions to that, and that is languages like Java, where they have their own intermediary like layers in here, which then talk to the operating system. Also, interpreted languages like JavaScript and Python, which do not compile, by the way, they don't turn into machine code. The instructions are converted on the fly to the operating system. Those also operate inside of containers, which then feed to the operating system, which is kind of interesting. Of all the languages you see here, the only one that's capable of directly talking to the operating system, by the way, are the C languages, most notably C and C++. And that's why those two languages are actually used for operating system development, where none of the others can be used because they don't have the capability to talk directly to the hardware. All right, some responsibility that comes with that too. But this is kind of interesting that many of the languages that we code in often push through the same layers of tools to run with the operating system. That's really the point there. Now, this next little segment that we're going to go through here talks about this thing called the fetch execute cycle, which is a process that happens on computers when they're executing the instruction sets that we create. And they make a point here. It says a computer constantly executes instructions repeated in a never-ending sequence. So whenever you boot up your computer and Windows is running, it is running software that is continuously going. So like many of us, and you guys might be like me, you might not even shut your computer off, right? Maybe the only time you reboot it is when you have an upgrade or something. Not sure if that's the case with you, but in the old days, people would always shut down their computers. Nowadays, a lot of people never shut down their computers. It really is a kind of a philosophical choice in some cases. I tend to be more of the type that never shuts it down, by the way. But as long as Windows is running on a machine, it is constantly doing stuff. Just right now, even this, okay, let's say I wasn't running a PowerPoint, the movement, it's just waiting for the movement of my mouse to see if I'm going to click on anything, or waiting to see if I'm going to hit the start key or the enter button. And so once a system is up and running, it is constantly executing instructions. You want to see how that process is going? You can right click on your taskbar, go to Task Manager. This is Windows only, obviously. Normally you see this in kind of a simplistic form, but you can expand it, and then you can look at all the different programs that are actually running on my computer. And it's like, oh my God, all this stuff is happening on your computer all at the same time. Yeah, it's running all these programs all at the same time. And you see I'm scrolling and scrolling and scrolling and scrolling and scrolling. And I'm zooming with you guys, and I'm recording video, and I'm streaming and doing a PowerPoint, and doing all these things, and my computer is doing all of that at the same time. It's very impressive when you really start to think about it. If you go over to the Performance tab, and I didn't mean to do that, let's reinitiate. I'm not sure how I got there actually. It's kind of weird. Um, and you look at the performance tab, it'll actually show you. You know, I'm not moving anything on the screen right now, but my CPU is certainly working. It shows you how much capacity I'm using up. It shows you how much memory I'm using, how much disk writing is going on. It shows you all those things. But you see, the CPU is at, I don't know what the capacity is here, about 25% roughly, yeah, 28, 30%. It's constantly doing stuff in the background. What's really fascinating about this little image here too is look at all the different stuff that's going on. There are 291 processes. Those are basically programs that are running on my computer right now. Some of those processes have multiple subprograms that run off of them. So I really have almost 4,000 programs running on my computer at the same time. And that's kind of mind-blowing when you stop and think about it. When, as programmers, we often learn how to write one program at a time, and then we're thinking of the fact, here's my machine running almost 4,000 programs simultaneously, and it's okay. The handles, by the way, this is the number of memory locations and things that we're moving around from the CPU to memory to the registers to the arithmetic unit, back to the CPU, back to memory, back to the hard drive. And these are all the different handles that are being moved right now. So 134,000 of those. And that's pretty interesting when you start to think about it like that. And so if you guys want to explore this, I think this is a really great tool to kind of learn a little bit more about your computer, by the way. But when we get into the fetch execute cycle, when we're actually running software, it basically works like this. The first thing that it does is it gets the next instruction, or the first one, right? Figures out what to do, pulls together the information it needs, it does it, somehow it saves the result, and then it does it again. And notice, repeat, billions of times per second. Billions of times per second. I just want you to think about that. That is mind-blowing. And we sit here and we get frustrated that our computers don't work fast enough, right? Because we're pushing them so hard. Some of the things that we're doing these days, especially with all this like online streaming that we're doing, really pushing the computers pretty hard. All right. As a graphic, if you want to think of it like this, and if you're formally studying computer science, by the way, you really go pretty deep into this stuff. This is the cycle. So you get the instruction, that's an IF. You decode the instruction, that's an ID. You fetch the data if you need data. So you might pull something out of a memory register, load it up or pull it from the hard drive into memory or from memory, whatever. Then you execute the instruction through the CPU, and then you return the result. And sometimes returning the result is just storing it back in memory or the hard drive or moving on to the next instruction. So that's the process. Now, keep in mind, whenever we're talking about this fetch execute thing, this is part of your homework, so this is pretty useful stuff, I think, at least in terms of getting the work done. When we start to look at like how the computer operates internally, there's some major pieces in play. And I want you to think back when we started talking about like computer systems and that system concept. And those of you that are taking the MIS class, I guess, Dennis, that's you. And we talked about like input, output processing. I want you to see, the input, the output, and then we have all these things up here, which are typically related to the processing. The control unit itself is the processor. The processor has a subunit called the ALU, the Arithmetic Logic Unit. In real old computer systems, this was actually an add-on. You have to buy that separately. Now they're built in. There's the memory, the RAM, and then the input and output mechanisms, wherever we're pulling the stuff from and sending it to. Those are the basic internal key components that make a computer go. If you start to look at that as a graphic, and I think they did a really nice job, I think, on these graphics. When you lay it out like this, you start to think about the pieces, right? So the first thing we look at is usually the CPU. So the CPU does all these things. It controls those portions of the fetch execute cycle. So you see the fetch, decode, fetch, execute, return, these things. Then you see the memory registers here. So like every spot of memory on your computer. So every time, think about this, anytime you create a variable in a program, like in Python, when you create a variable, you're storing it in a memory location, and that memory location has an address. and that will have a certain amount of data put into it. And often when we're executing instructions, one of the things we're doing is we're fetching the instruction where? From memory or from input or output. And I want you to notice the input and output pieces, right? Some of these things fall into both categories. So we have like, things like storage devices, flash drives, hard disks, SD cards, whatever, can both store information, so they can be both input mechanisms and output mechanisms. And then we also have things that are dedicated to either one. So typically like the keyboard, mouse, mic, camera, all those things. Output devices, typically a display screen, a printer, the speakers, maybe the vibration of the haptic feedback on your mobile device. All those are output devices. All of those interact. Ultimately, when you're executing instructions, sometimes you're doing math, so then you go to the arithmetic logic unit to have that happen. You'll see there's all these little pathways here. That would kind of be a primitive way of signifying the bus system, which is the connections on the motherboard that connects the pieces together, and how it travels. Now, very interestingly, because I'm kind of actively shopping for computers right now. I'm looking to replace my laptop and maybe even one of my desktops here, because I'm finding that I need more horsepower. And I don't know if you guys are feeling the same thing these days. And what a lot of people, when they look at specs of a computer, they just look at the CPU and the RAM and the hard drive and go, oh, it's got an i7 and 16 gigs of RAM and a 500 gig SSD. That looks good. But one thing that they often ignore is what kind of motherboard it's built on top of and the impact that has on the system. So often I hear this argument from people. It's like, you're overpaying for that Mac. You barely have half the capability for twice the money. And then I'm like, you're ignoring the subsystem it's attached to, because the Mac subsystem typically and always has operated significantly. They've always had better motherboards and ones that were designed to work with their stuff, and they will always work faster. But that's a really important thing when you're doing this. So this is, I think, a very nice graphic. Start to break these down piece by piece. So the memory subsystem is basically where we put stuff. Everything that we do on a computer, some will have to travel through memory, right? So if you boot up your computer, the operating system loads up into memory and then executes its instructions. If you create a Word document, you're typing, it's mostly in memory. When you hit save, it stores to the hard drive. And so memory is really important. Memory is broken up into pieces. So all the RAM that you have on a machine is broken up into little segments, each with its own memory address that the CPU can directly address. And so it can move stuff into that location, pull it out, shift it around, add them together, do whatever it needs to do with them. And then what do you put in those memory locations? Well, it depends on what you're doing, right? So it could be numbers, it could be words, it could, be portions of images or whatever. But ultimately, everything kind of boils down to binary, and its representation in a binary format. And that's what this is about. So typically, there's standard allocation sizes for memory on both in RAM and on a hard disk. So there's certain like minimum chunk sizes that you get. We often think about bits and bytes. So one bit is one binary character, a 0 or a 1. We combine 8 of those, we have a byte. You take 1,024 bytes and you have a kilobyte. You take 1,024 kilobytes and you have a megabyte, and you go up the chain to, gigabytes, petabytes, terabytes, et cetera, et cetera, et cetera. But interestingly, every time you guys are using a keyboard and you press one key on the keyboard, that generates 8 electronic pulses or 1 byte of information. So every key press is 1 byte. And those 8 binary bytes using the ASCII system can generate any character on the keyboard, upper, lower case, the numbers, the extended key codes, the shift key, arrow keys, anything you got on your keyboard can be represented with 256 different variable numbers that fall into an 8-bit or 1 byte range. It's pretty amazing, right? You think about how fast you type, every key press is 8 electronic pulses. Amazing, really. All right. When we start to work with memory, I think what's kind of interesting about memory and a lot of people don't know this, is you can put stuff in memory, but why do they call it RAM, right? What's the random access thing all about? So let's think about the old days, like if you were playing a cassette tape, right? And you put a cassette tape in your cassette deck and you hit play. If you wanted to not hear the first song and you wanted to go to the second song, you'd have to fast forward and hopefully you found the right spot, unless you wrote down what the counter settings were or something. It would be difficult to go exactly to the song you want. But then all of a sudden they came out with CD players, and all of a sudden you could like skip a track and go right to the beginning of the second song. That would be an example of random access. I could go directly to the spot I want to go to. And so when we say RAM, that's really what we're referring to, is we have the capability to directly address any memory location, and it doesn't have to be sequentially. It can be, I want to go to the first one, I want to go to the last one, I want to go to the middle one, I can go to any one I want and do whatever I want with it. And so that's what we mean typically with RAM. These days, I think we find that a functional minimum of RAM for most computers is 8 gigabytes. And if you're working with anything less, you really need to jump up, real frankly. I would say that a functional minimum these days, if you're out shopping for a machine, is 16 gigs. That's what I would recommend. If you want to prepare for the future, go 32. If you really want to prepare for the future, go 64. But 16 will do you well for a while. I've been at 16 gigs of RAM now for well over 5 or 6 years, and I'm finding it limiting at times, folks. I max it out pretty often. You guys saw what my hard drive space looks like, so it doesn't take a lot to push it hard. Do a little video editing or something like that. Fire up a couple of IDEs, pull up a Zoom session, video record. That RAM's jumping way up there. The control unit subsystem, that is the thing that really drives the whole thing. And so that's a special part of the CPU that basically grabs whatever the next instruction is and operates it and works on it. So the control system is really critical. And that's really the job of the CPU. What does the CPU do? It processes all the instructions. That's why they call it the CPU, Central Processing Unit. But there's the control unit is a subsystem of it, which executes the actual instructions. Then we have what we call the ALU. And I don't know if you guys heard me before, but in the old days of computing, so for example, when I bought my first desktop with my own money, I was so proud. I went out to Best Buy and I bought myself like an Acer 486 SX25. I remember it very succinctly. I couldn't afford the DX model. The DX model included the arithmetic logic unit. And of course, they had a little slot on the motherboard where I could add one. And what that would do for me is it would allow mathematical operations to happen faster and more efficiently and give my machine more horsepower. I couldn't afford it at the time, so I didn't get it. Right? And a lot of people would make the same choice. These days, all modern processors have this built in, by the way. So it's not something you can buy as an extra. But that part does separately handle the mathematical operations. In fact, it's streamlined just to do math. And I think that what's kind of interesting about it, notice it says it carries out each machine instruction with a separate circuit. So in many cases, it can do multiple operations simultaneously. So how is it I can move my mouse, watch a video on the other screen, record myself, do a PowerPoint, broadcast my voice, all at the same time? There's a bunch of math happening in the background. ALU is helping make all of that work simultaneously. It's pretty interesting. It uses this thing we call logic gates. And of course, if you guys are familiar with programming, you know what and or is, but those operations are built natively into the chip, which is kind of fascinating. Not in the same way you use them in programming, though, by the way. There's the input and output subsystems, and basically these are the pieces that connect out to the physical world, so the physical devices, the hard drives, the memory, the printers, the keyboards, whatever is on the outside of your machine. And the kernel of our operating systems is directly responsible for communicating with those devices. And that, in fact, that's one of the primary things that it does, is tells the system how to do that. All right, let's move on to the peripherals. So peripherals, typically are, most of the things we think of as being outside the computer system. But I do want to kind of qualify that a little bit, because a lot of the things that we consider part of the computer now used to be considered peripherals. And one really great example is in the old days, you'd buy like a PC desktop. It wouldn't even have a sound card. You wanted sound? Well, you have to buy a sound card. So that was considered a peripheral. If you wanted to hook up a printer, that's a peripheral. Of course, those aren't built in, but sometimes CD-ROM drives, microphones, cameras. I mean, these days we buy a laptop, the camera and the mic are built in. But if you guys are on a desktop, and some of you might be, you might not even have a camera and mic, right? And you have to go out and you have to buy a little webcam or something to add to your system. So those are important too. But they are, kind of physical things. There are some special categories, and I think they make a nice note here that some things can be both input and output devices. And I think of disk drives, and stuff where we can read and write to them. And it's really that read-write capability that makes them both input and output. So we can feed in information that we need as an input, like what software we're running. And then we can write back the files we create. So yes, they become both input and output. Monitors, for example, can you imagine all the processing that goes on just to process all the bits on your screen? I want you to kind of contemplate this for just a second. The screen that I'm sharing right now is 1600 pixels across by 900 pixels down. And over here, I got another one that's an HD monitor, which is even more. And my machine, on a second by second basis, and I'm only using a refresh rate of 60 hertz here, right? So 60 times a second, each one of those pixels is being rewritten. So if you do the math on that, what's 1600 by 900? A lot. What's 1920 by 1080? That's a lot. Add all those together. So you got tens of thousands of pixels that are being redrawn 60 times a second relative to what we're doing on the screen. And that's all happening, so fast. And we don't think about it, folks. We don't think about it at all. But I think it's fascinating to try to think about it. Peripherals often, do things, for example, some peripherals, we take this for granted. We just plug them into the computer. It makes a little beeping sound and it works, right? We can plug in a hard drive, for example, or a flash drive, and it just recognizes right away and it happens. The interesting thing is that wasn't always quite so easy, and I always like to share those stories with people so that you don't take for granted what we have sitting in front of us right now. There was a time, for example, like if I wanted to put a computer on the network to print or to connect to the internet, it was like a half-day affair to load the drivers, get them to work, get the right settings, test it, probably failed half the time, probably have to reboot like 20 times. It was a nightmare. Now we very simply go out to the store, we buy something that works with Windows, we plug it in, and there it is. Probably don't even have to download the drivers for us. Windows does it automatically. But most devices typically need to have drivers in order to be able to talk to the operating system correctly. And that's a pretty fascinating thing. Now, when we're starting to write computer programs, ultimately, whatever code we write, whatever language we use, will typically be what we call a high-level language. So if we look at like Python, for example, where we have commands like print, and then you parentheses, double quotes, and put your message, and it ends up on the screen, right? But what's happening in the background is that code is being delivered through that software stack down to the operating system, turned into machine code, which looks kind of like this. This is machine code on a high level. It looks like assembly language to me. And then that's turned into binary, which looks a lot more cryptic. And unfortunately, humans can't really read it, right? But in an example like the one that I highlighted with the highlighted text, this is a command and a memory location. So we're adding what's in memory location, whatever. And then this command, this is actually a conglomeration. So it's saying add this memory location and this memory location and put it in this memory location if you read through this, right? And that's the kind of programming we would do with assembly language, real close to machine language, Not quite machine language. We're really, really close. Very primitive commands. Now, what does that mean that it's doing? Well, we don't know. It depends on what's sitting inside those memory locations. It might be numbers. It could be words. It could be video. Who the heck knows, right? From there, we kind of start looking at, this aspect of the PC called the program counter. And this is the one that basically starts to step through each piece of the instruction set. So this keeps track. Like it says, it's the counter, and it says, well, okay, we're doing this now. Okay, next, now we're doing this, and it's keeping track of each click of the clock. Now, by the way, how do you know how fast your clock is clicking, right? That's a really kind of weird thing to say. But if you start looking both here, right? So you're looking at the basic stats for your system, and you look at this little stat right here, right? This is the base speed of your CPU. And this is indicating that there's 2.2 gigahertz. Okay, so what does that mean? That means roughly 2.2 million, or is that billion, instructions per second. Clock ticks. That's how many steps are happening per second. And this is only, frankly, showing the total CPU utilization. But the reality is I have a quad-core processor, so 4 64-bit processors working in tandem, which breaks down to 8 32-bit processors all working simultaneously at that speed. And this is, 7, 8-year-old machine, folks. It's pretty old, right? And so this kind of shows you how many are running at the same time. You can also get that information if you're curious about your system, where you go to this PC on your computer, give it a right click, choose the properties, and I think we've done this before, and you can see your CPU type and speed, which is pretty interesting. And this is really one of the more important factors when you're shopping for a computer, right? Is like what your CPU really is. Because you can look at the gigahertz speed of your CPU, but if you're not comparing apples to apples, right? So if I have one CPU operating at 3 gigahertz, but it only has 4 cores, and I have one at 2 gigahertz running 8 cores, which is faster. The one with 8 cores is much faster because we're multiplying out, and it becomes a whole formula, frankly. And it takes a little bit of study to know which CPUs to buy, by the way. Right. So when you start doing the program counting and stuff, sometimes you are running things in a sequence. So when you learn how to program, you learn that one of the logical ways to solve a problem in programming is through a series of steps. But there's also the capability that sometimes you get to a spot in your program and you have an if statement, for example, and then you are basically forking the road, which way are you going to go? And that's what this is talking about here, is the program counter also allows you to do jumps or branches, to jump to other locations out of sequence of the program count, depending on the instruction set. So this is kind of a little bit of a mind bender. When you start stepping through the command that they were talking about, they start talking about, how it works on a real minute level. And then they go into these graphics where they say, okay, so first we're the program counter's at 800. Which instruction are we addressing? 800. And what is the instruction that's stored there? Well, we've loaded it up, and this is the instruction, the one that we've been looking at. And you see that one gets loaded into memory, and then it gets executed in the CPU. And it kind of steps through this process. Now, depending on what happens with that instruction set, it could be addition, and that's the example we're using here. From there, it starts to move in, then up to the math unit to do the process, dealing with multiple addresses. And then finally, after it does it all, it will start to put it back here, and it fetches the data to do the math. So these are the numbers that were actually stored in those locations, and it's doing the math, so that's why it's listed here. And then from there, we do the next thing, and once you have the result of the math, then you have to start to come up with the result, and the result then, of course, has to be returned back in, and then it gets written back to a different memory location, in this case, memory location 4000. Now, the fascinating thing about your operating systems and why we even have them is the operating system controls how the stuff is written and where it's written to in memory and keeps track of all of it, right? Remember, the hardware is just a dumb machine. So the operating system is really responsible for traffic controlling all of this. So when you think about all the stuff that's happening in the background in your machine, I want you to contemplate some of this. This is pretty bizarre kind of stuff, folks. And that's kind of where they go next with this. So when you think about what you're doing on the screen, and especially when you start to do more powerful things, the reality is that all the tasks that happen on our computer do break down to really, really, really simple operations. It's mostly what you just saw. Pulling something from memory, adding it together or subtracting it or whatever, writing it back to memory. And so if you think about that, and it's like, that's what drives the whole computer. So how do they get it to do all this? Well, it's complicated, right? Because all those little bits and pieces have built up over time. So when we looked at like those charts of like ENIAC, or those pictures of ENIAC where they're plugging in cables and flipping light switches and whatever, real basic operations, and all they were trying to do is like a simple math problem. We're doing simple math problems, watching Netflix, chatting with our friends, and posting a video on YouTube or whatever, all at the same time. But the reality is, it happens really, really fast. A lot of simple operations combined together to create something super, super powerful. And on top of it all, we take it for granted, which I think is even more fascinating. They do talk here a little bit about the the gigahertz, megahertz thing and the clock cycles. But the clock cycles are also relative to how wide the data path is through the device. So the more CPU cores you have, and the faster motherboard that you have, and the faster RAM that you have, the faster all of these operations become. And so if you are shopping for a machine, if you're in that mode, you have to consider really all those aspects. One trend that I kind of don't like as an old school computer person is I'm seeing a lot of machines now, even PCs, and Mac went this way first. They're soldering all the components onto the board. I can't change the hard drive. I can't change the RAM. I can't change anything inside the machine, right? Whereas if I'm kind of leaning towards like building my own on a desktop at least, there I can select the power supply, the motherboard that I want, the video card I want, the CPU I want, and optimize it and get really good performance. But these clock cycles sometimes can be a little bit deceiving in that regard. So let's get now down to the point where we start thinking about what the programmers do. And when we sit down as programmers and write code, we might write some code that might look like this, and this is could be a number of different languages, most likely probably Python or well, no, they don't use this in Python, right? They use self in Python. But it's a high-level command, still a little bit cryptic to people who aren't programmers, but the people who are programmers, you can kind of, all right, you're setting some sort of a variable and you're adding to this variable here 0.02, a floating point number. Now, ultimately, all of these commands break down to machine code, binary code, and then are translated into what we call assembly code, which looks a little bit more like the thing that we're pumping through the CPU. And the commands are almost always add, retrieve, and store. Those are the three commands you use in assembly language, because that's basically all you're doing. Now, when we start taking a program that we've written and we're trying to make it execute on a computer, it's either going to be interpreted or compiled. And so I just want to clarify again, JavaScript and Python are classic examples of interpreted languages. They do not turn into executable files. They just run. The operating system handles all the conversion. The compiled programming languages like Java and C and C++ and C# and Visual Basic, and others in that category do get converted, but they go through assembly language first and then go through the compiler to ultimately start converting it down to even a lower level, zeros and ones that the computer can actually push through electronically. So ultimately, it all has to be turned into electronic pulses, positive or negative voltage of plus or minus 5 volts, by the way, and that is what runs our computers. And I think that is just fascinating when you start to break it down. And I'll tell you, if you're really fascinated by this aspect of computers, computer science might be a good path for you. I'll be real frank. There's not a lot of people that like to think on the circuit level, but when they do design CPUs, this is the kind of thing that they're thinking about. How are we pushing the instructions through? How can we make it faster? What limitations do we have? How can we overcome those? And when you start to think that a CPU has literally billions and billions of transistors, and remember, if we kind of correlate that all back to like ENIAC, right, with the vacuum tubes, each transistor is a vacuum tube, right? It's astounding that we put that all on a little chip that I kid you not is like about a little bigger than a quarter, and then on a platform that's a little bit larger, and that's all inside there. How did we do that? And how is that powering our computer systems? It's a pretty interesting thing. All right, folks, that ends the lecture part here. So this video is now over.